today we're going to talk about notes, and the notes are going to be about energy, so maybe I should have a little... Hey, all right, so we're going to talk about energy today. Hopefully I have more than that. Energy is actually a relatively easy concept all by itself in terms of the math. The math in this chapter, easy. My expectations for everyone in the room are no less than A-. I know, a couple people just were like, don't you do that? Don't you lay that guilt on me? Yeah, I just did that. Yeah, I just did. Yeah. This chapter, the concepts are things you've been hitting since second grade. My son had to learn these terms in second grade last year. All right? That's not to make you look at kinetic energy and go, I don't know what that is, and make you feel bad, but just to know that somewhere in the back of your brain, a lot of these terms already exist. So we're going to try to go back over them from a slightly higher level perspective, not the second grade level. And we're going to talk about them in two directions. Some of these are very much physics terms, and you may have learned about them in your 8th grade physical science class, and you haven't seen them much since then. Some of you are taking physics again next year, and you will see them again a lot. Let's talk about these two terms in terms of standard physics. So, 3 people climb a tower, and there are windows, and each of them have a baseball. You have person A, person B, and person C, and they're all holding their baseball out of the window. Which baseball has the most potential energy? C, because it can fall the farthest, right? What was that? Weird. There was a minor earthquake in the class a second ago, localized around one student. So the ball goes out, woo, boom, 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 boom. Ball goes out, woo, boom, 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 boom. What happened to the sound effect? All right. Lastly, which one had the most kinetic energy right before it hit the ground? Once it hits the ground, everything gets wonky. But just before it hit the ground, which one had the most kinetic energy? C again. The potential for movement versus the actual movement. Kinetic energy is usually described as the potential to do something versus kinetic is actually doing it. And some of you have lots of potential, and if you don't use it, though, it's wasted. True? And there's all ways of wasting it. Insert picture of people texting on their phone here. I wasn't looking at you. I don't know why you give me that guilty face. So, what is energy? Energy is the ability to do work or produce heat. A lot of people talk about, when you move something, you're doing work from one object space to the next. If you put heat into it, you're expending energy by friction or something like that. But again, that's all like a physics description. Let's talk a chemistry description. He has a Nutri-Grain bar on his desk, which is a great prop for this conversation. This Nutri-Grain bar has some calories in it. Take a guess how many calories are in here. What the hell? How do you know 120? Yeah. That was freakish. She said 120, and it's 120. Actually, in chemistry land, this is 120,000 calories. In chemistry, we do it right. This is a dietary calorie. When you look at these calorie counts, they're called dietary calories. This is actually thousands of calories. But when you start adding thousands together, a lot of people's brains just give up. You go like 4,000 plus 2,000 plus 700,000. People go, shut up. Those numbers are too big. And so a long time ago, when the FDA started slapping calories on there, they started off by doing kilocalories. This would have said 120 kcal, and people know that K means 1,000, and so they kept trying to convert to 1,000 and then add them together, and they gave up after a while. So instead, they just capitalized the C and then were quiet about it, because the numbers are easier to add when it's 120 plus 200 plus 400 plus 1,700, because you just ate like a Big Mac with extra cheese and stuff. But these are a great example of which of these? Is it kinetic energy or potential energy? this Nutri-Grain bar? It's potential. It gives you the potential to do something, right? It gives you the potential to catch an object. If you don't have a source of potential energy, your movement equals zero. You are constantly expending energy to do everything you do. You are converting food into motion, into thoughts, into nerve endings, firing, into everything. If you eat nothing, you have no energy, your body shuts down, which has a name called death. You have to have an energy source. You have to be able to process things. Some of us are storing it very well all over the place, and that's potential for future use, right? And that's the whole reason we have fat on our body, is we're storing potential energy so that we could later on use it if necessary. That kind of a chemistry perspective on the same idea. Law of conservation of energy is also a big deal, and it's also related to another law. What's the other big law? Law of conservation of... This is the law of conservation of energy. What's another big law of conservation law? Law of conservation of mass or matter? Yeah, that's the other big one. And they're actually interrelated. Energy equals mass times C times... Yep, that's that thing that Einstein came up with or worked out. It's actually drastically more complicated than that. But the two laws are interrelated by that. Energy can be converted to mass, and mass can be converted to energy and back again. It's just not easy to do. But this idea, it was just demonstrated by the awkward handshake between you and I, right? You were stealing my energy. The energy I had was being transferred from one object, my hand, to another, your hand, but it wasn't being lost. Was the energy from me going anywhere else other than into his hand? The air. That's the other thing my hand is interacting with, right? The air. So it's not all going into there, but none of it's being lost. It's always going from some place to another place, and this energy slowly spreads out. All right. Other concepts we are okay with but don't quite understand is work. Work is applying a force across a distance. It's moving things. It's actually expending energy for some purpose. Again, if you lift something up, you're exerting a force, you're moving it, you're using energy. What's really complicated about that, though, is to think about when you pick an object up and move it, what is going on chemically is so ridiculously complicated. It's not simple at all. We can't get into it like on the real picture. But you just digested food and converted that food from what's called adenine diphosphate, adenine triphosphate, which is an energy chemical, and you're storing that energy chemical to later be used and then expended. And what happens if you expend too much energy and keep doing that forever? Have you ever worked out so hard that your muscles fail? Have you ever run so much that you cramp up? Who's ever had a Charlie horse or a cramp? They are the worst, aren't they? Yeah, Charlie horse is when you aren't getting enough of the right chemicals to those cells in a speedy enough fashion, and the cell keeps doing a reaction, runs out of a basic reactant, and pulls something else in, and then it starts producing an acid instead. And you get lactic acid to build up in your cells. And the burn you feel in a Charlie horse is actually the acid burning the muscles. It's actually burning. And the chemicals are destroying the cells, and you're like, oh my God. I remember one time I did a throw-in in soccer, and as I did the throw-in, both of my legs went into full cramp mode. It was a beautiful throw-in, and the follow-through looked impressive because I went all the way to the ground. And then I cried, holding my legs, like, oh God, what's going on? And it takes a while for your body to get the right chemicals into there to clean it out. Temperature is something a lot of us don't understand. People have an object of temperature as, it's the thing on the probe that's under my tongue, right? Why is that most people's image of temperature? That's the most common way you see it, right? Very good, yeah. So what I think of as temperature is I think of a particle moving back and forth. Temperature is actually speed. It's how fast the particle is moving. So I just had this particle moving back and forth with a certain speed. Now I have another particle moving back and forth with a certain speed. Which particle is moving faster, brown or blue? Brown. If these particles come up to each other and touch, the ones that are moving faster and the ones that are moving slower start to fight each other, and the ones that are moving faster are going to hit the slow ones and make them start to move faster. This is basic energy transfer at the surface. The atoms hit, and the atoms hit. These are going to hit those and make them move faster, and conversely, when these make those move faster, the brown ones are going to move slower. And eventually, the temperature, let's say this was a temperature of 25 degrees Celsius, and this had a temperature of 20 degrees Celsius. As they interact, the one will drop and the other will rise, and eventually both of them will have the same temperature. Let's pick a temperature that might be appropriate. What might the new temperature be after they've touched for a long time? 23? Why do you say 23? It's in the middle. Yeah, it's going to be somewhere between those two. It's not going to be higher than either of them. It's not going to be lower. It's going to be in the middle. It's going to be somewhat of an average. And there are a couple different things to determine where the average would lie. If you had an equal amount of both, it would be an average of them perfectly. But if you have a heavier quantity of the fast one, it would be closer to the heavier side. So, heat. Heat is actually what just happened there a second ago. So the hey, we're going to hold hands for a second. It's going to be fantastic. Not going to be awkward at all. Vahar, her hands are the polar opposite of yours. Like, this is a warm handshake. Does my hand feel like an ice cube? Yes, I know it does. Yeah, I keep them in ice just for this moment. So right now, the temperature in my hand drastically lower than the temperature in her hand. At the surface, those particles are hitting my particles and making them move faster, and energy is being transferred. And we have a term for energy transfer, and it is heat. Heat is the flow of energy due to a temperature difference. Now, we have a couple other common terms which are completely useless in the land of chemistry. That feels hot. That feels cold. Those terms are pretty useless in chemistry. Don't ever say something feels cold, because that implies that it has no energy. Right? When something feels cold, its temperature is lower, so its particles are moving slower. If something feels hot, its temperature is higher and its particles are moving faster. Yeah, might have actually made it on there. Yeah, faster. At least I think that recorded as like flack or something like that. And then it gets to the who's endothermic and who's exothermic. So let's see. Here you go. Hold this. And then you have to tell me whether or not your hand is endo or exo. So he holds this, and he would be exothermic if that felt colder. He would be endothermic if that felt warmer. Because if that object is warmer, the energy is going into his hand. So does that object feel cold or hot to you? Cold. But I don't want him to actually ever say cold or hot again. I want him to say it's endothermic or it's exothermic. So if it feels cold, the energy is leaving his hand and going into that big chunk of aluminum. So you are currently exothermic, aren't you? And it is endothermic. If it is getting warmer, it is endothermic. Now in a minute, we're going to take this big chunk of aluminum and put it in the oven. I just want to point out that it's almost solid. It has a giant hole here and a tiny hole here, right? Can you see that? All right, because we're going to do a couple things with the oven in the back. Exo and endothermic mean that energy is flowing out or in. It is not uncommon for us to actually do this as a demonstration in the fume hood. I'm going to draw a picture and then ask you to identify what this is a picture of. Let's go to you, sir. What do you think that's a picture of? No, not a triangle. Come on. Dorito. Very good. It is a Dorito drawing. And it's a pretty good Dorito, right? Yeah, I know. I'm 4 years of high school art. That's me. Yeah, that's good. We will light it on fire on one side and then remove the match and let it burn. And the energy from the Dorito will slowly be released. And it will warm up a beaker or test tube above it. and we'll know how much energy that water is gaining. Where does the energy this water is gaining coming from? The Dorito. And then we'll know the amount of energy the Dorito has stored in it. And we call that amount of energy stored in it calories, which is how they calculate the amount of calories inside food, is they burn it. So it's a little bit more complicated than burning it underneath a beaker of water. We use what are called bomb calorimeters. A bomb calorimeter is a container inside a giant container, and the internal container has usually gasoline or ethanol in it, and you burn the gasoline or ethanol and you measure the heat that goes into the outside container. Then you do it again, but you throw your Nutri-Grain bar or your Dorito in there, and you measure how much additional energy came out. Because as the ethanol burns, it's got enough energy to also burn that. And then there's going to be the ethanol's value plus the Nutri-Grain bar plus the Dorito, and you're going to get this extra energy that comes out, and then we measure that as calories. The big problem I have with the calorie content on everything, this is just my personal opinion, we've stepped outside the realm of this class, is that the way I break down those calories and the way she breaks down those calories are completely different because we have different enzymatic backgrounds, and our enzymes bond to those things very differently. If I'm a diabetic, I don't necessarily deal with sugars as well as someone else that's not a diabetic and things like that. So those calorie values are very deceptive. They don't really mean the same thing to every single person on the planet. So energy is the ability to do work. We need energy. Make sure you eat a good breakfast. Let me pause as I go on a breakfast rant. And that's probably the most important lesson in life right there. So, calories and joules, what the heck? These are both ways of measuring energy. We got one right. We got a unit right. Yay, America. Woo! The calorie is a better, more common sense unit than the joule, which is the one we're going to use. But let's talk about why the calorie is better. If you put a calorie of energy into a gram of water, the gram will change. Oh, this should be like an arrow. If you put a calorie into a gram of water, its temperature will change by 1 degree Celsius. Those are pretty numbers. 1 into 1 changes you by 1. This is a chemistry calorie. If you're looking at that Nutri-Grain bar and it's 120, capital C, that would be 120,000 calories. Would take a gram of water and increase its temperature by 120,000 Celsius. That doesn't seem very logical because it would probably boil and whatever. But that's the idea. The joule is the SI unit. That's the one we will use the most. Same idea if you put 4.184 joules into a gram of water, then its temperature will change by 1 degree Celsius. It's just that it's 4.184 instead of a nice even 1. The joule is based off of mass times acceleration. It's based off of the standard units like meters and per second squared and kilograms and stuff like that. So we need to be able to convert between both of those. So I'm going to pause while you guys work out these two math problems using the equivalency. For that. So I wrote down the given, and then I used the units to convert. The 4.184 always goes with the joule, and the calorie always gets 1. Hey, Mr. Murphy. Yes, Jay. Those both say kilo. That's awesome. If they both say kilo, we don't have to then like switch to 1,000 and switch back again. Technically, if it had been, you have kilojoules to calories, we'd have to switch to 1,000 and then do the slow switch. That would have been annoying. And then down here, we'd have 1 calorie and 4.1 to the 8 to the 4 joules. And let's call on people with calculators out. Do you have this one for me? Do you have this one done? What is it? 1.36 or 1.4. Both of those I'd be very happy with. And what about this one right here? Pocket. Say again. That'll work. I believe you are correct. So converting between calories and joules is a pretty common thing. A lot of our math problems will be in joules because that's the standard unit for all of science. But switching between the two is so super common that we're going to throw that up there. Do I need to know this number? Yes, guy in the tuxedo with the red hair, you do need to know the number 4.184 is the same as 1 cal. It also happens to correspond to something we're going to use with water, so we're going to use that number in a couple different spots here. We're going to talk about energy a great deal, and measuring energy is kind of a weird thing. Here are 2 pieces of aluminum. In my left hand, I have aluminum foil, and in my right hand, I have a cylinder of aluminum. Which one would be harder to warm up? The cylinder, because it's heavier. Let's hear the distance again. Here's the sound difference for you people at home. There we go. Give you a good sense. This is 500 grams. This is 2. So if you wanted to warm this up, you're going to have to put way more energy into this. Now, where the question gets a lot harder would be if I held up, and this is not made of lead, but just for pretensies, if I held up a same mass-sized piece of lead, and I said, lead versus aluminum, which one would be harder to warm up? You probably have no experience to know which one, right? You're like, 50-50, I'm going to go lead, or 50-50, I'm going to go aluminum, because you don't have any experience with the substances enough to know that. But do you think the type of substance matters? It definitely does. So there's 3 things that matter as to amount of energy. How heavy is it? Is it 500 or is it 2 grams? How much do you want to change the temperature? I believe she would like me to change the temperature of the room by 5 or 6 degrees, right? Kind of chilly right now, yeah. And then what is the substance? Is it aluminum? Is it lead? Is it air? Is it water? Is it a frog? You know, what it is might matter as to how much energy you put in it. And because we're chemists, we've got an equation for that. This equation, Q equals mcat, is usually how it's said, just for remembrance sake. Typically, Q is a lowercase q. I don't know why it's uppercase here. I think the typo just kind of like, is it lowercase or uppercase? Okay, good. Yeah, it's typically lowercase. I don't know why it appeared uppercase here. Q is the symbol for energy. Just think about how you spell energy, E-N-E-R-Q-Y. If you're dyslexic, that makes perfect sense. If you're not dyslexic, you probably see a G there. But so Q is energy. C is the capacity of that thing to take in energy. Is it lead? Is it aluminum? Its capacity is different depending on the substance. How much mass does it have? And then for a lot of you, this weird triangle, the random appearance of a triangle, might be confusing. That is the symbol delta, which is the same as change, which kind of implies that a certain airline is asking you to change to their airline. And they felt that that was a good representation of what they implied, like we represent change, we are delta. But now you've been around for like 30 years and you don't. So we look at the change in temperature. Currently the room is about 20 degrees Celsius. Naya would really like it to be 25 degrees Celsius. She wants the temperature to change by 5 degrees. She wants it to increase by 5 degrees. On the flip side, Jaden back there, Jaden's wearing like 4 sweatshirts, a hoodie, he's got earmuffs on, sweatpants, snowsuit. He is hot. I know you're not really. This is fictitious. You're not really. I can tell. The initial temperature of the room is still 20. He would like it to be 10 based off of how he's dressed. He would like the temperature to drop by 10 degrees Celsius. Delta T could be positive or negative depending on how it's changing. So when I held your hand earlier, hey, how's it going? Holding hands. It's warmed up a little bit. But his hand still feels cold to me. He is taking in energy. His delta T is currently positive because it's gaining in temperature. My delta T is currently negative because I'm decreasing in temperature. Right? So what we're going to do is a little demonstration. Here's some heat capacity values. Which of these, and it's cut in half. Which of these substances requires the most amount of energy to change its temperature? Or to put it in a different way, which one has the highest heat capacity? Water on this list is the highest of them, isn't it? Which one has the lowest heat capacity, meaning the smallest amount of energy will change its temperature? Gold. Gold, it's easy to change gold's temperature. You put a little bit of energy in, its temperature changes. You put a lot of energy in, its temperature barely changes. Different example. Let's say that Yasmin has a pot of water and some gold jewelry. She sets them both on the oven. She turns the oven to 10. On the stovetop, on the oven. Who sets things on an oven? She puts them both on the stovetop and turns the knobs to 10. Energy is going into the water and into the gold. They're both gaining the same amount of energy. The gold's temperature is going to change a lot more. The water's temperature is going to change a lot less, even though they're gaining the same amount of energy. And the gold will melt pretty quickly, too, if you warm it up too much. So you'll have a puddle and some angry parents also. So what we're going to do here is I'm going to do some stuff with the aluminum chunk. I'm going to pause it here as we slowly we're putting some energy into that. The aluminum foil is also 22.5 degrees Celsius, but it is only 2 grams of aluminum foil. They are both aluminum, so they both have the same heat capacity. They're both increasing in energy. We will see what happens in a minute. While we're waiting, though, here's a problem for you to try. Who is Q? Who is M? Who is C? Who is delta T? Write them down, and I'll call on 4 very excited people. People wearing blue shirts today. Feeling good about blue because these are blue. So the delta T is always the final value minus the starting value. The starting value is 21. The final value is 32. How do I know that? Because it's going from 21 to 32. It's increasing by 11 degrees Celsius. Now we plug them all in, right? We have the C, the M, the delta T. It irritates me that I typed them in the wrong order. Is it irritating anyone else that they're like, this is C, this is M, and that's delta T, when the equation is that? Sorry about that. Support our troops. Support the troops. Can you give me the Q then? As in the answer, yes. What is it? And I rounded it to 2 sig figs, so I did 8.1. Same idea, though. Again, sig figs, just do your best rounding. Unless you're egregiously off, I don't pay too much attention at this point. But why? That has 2 sig figs, so I only wrote down the first 2 and moved on. Why is the unit joules? Where'd the grams and the Celsius go? Great question. We just did joules over grams in Celsius times grams times Celsius. So this grams on the bottom cancels that one. The Celsius on the bottom cancels that one. Joules don't get canceled. So cancered? Joules never get cancered. They might get Taurused or Gemini'd, but they never get cancered. No, the joules don't get canceled, therefore they're in the answer. Blah. How's that sound? This example is solving for something completely different. I'm going to find the values and plug them in there for a second. So, Champ, what's Q in this question? It is. It's the energy. Unit for energy is joules. How do I know the unit for energy is joules? Because the energy for unit is joules or calories. A-double-N-A. What is C in this question? Anna, what is C in this question? We don't know that. Do we know the mass? What is it? 2.8. Good job. What's the delta T? 15. It is a positive 15. It is getting hotter. It is increasing in energy, so it's positive. From here, you have 2 choices. You could either plug them in and solve for C, or you could arrange for C and solve for C. But either way, you should get the same C value. Either way, you get 0.24. Hey, Mr. Murphy. Yes, person with glasses on. I have it set up right, and I got a completely different answer. Chances are, when you divided, you moved the entire screen around. Just a second. Chances are, when you divided, you didn't divide by both things. You did like 10 divided by 2.8 times 15. So your answer's off because you didn't divide by both pieces. Good luck out there. Have a good time. So now that we know the heat capacity for mystery substance is 0.24, I go back to this chart. What is the mystery substance if the heat capacity is 0.24? It could be silver, right? This is one way you could identify if your jewelry is what they say it is, by heating it up and measuring the temperature change, or just hiring somebody else. It'd actually be very easy to do density instead. This would be a little bit complicated. But, you know, some people have used this. It's not uncommon to buy copper jewelry that is plated with gold. And so it looks like it's pure gold because it is on the outside, but the inside is copper. And so would its heat capacity be closer to gold or copper if the inside was mostly copper? It would be in between the two somewhere, but it usually the copper jewelry is a lot of copper and a tiny amount of gold on the outside, a thin candy coating. That's why it looks so cheap. Oh, it's time to do this. It's time to pull our aluminum out of the oven. So the temperature is exactly 53 now, 5 minutes later. And we could do the Q. We could say Q equals 500. I'm hoping one of you all is going to grab a calculator and do this math because I cannot do this in my head. What is 53 minus 22? The initial subtracted from this final, it's like 31 and a half? 30 and a half? 30 and a half? So 500 times 30 is like 15,000 times 0.89, like 14,000? What is it? Slower, man. Okay, so we have a lot of numbers up there, and I think we all agree that this number's pretty unreliable, right? Is it higher than that now? Okay, so that number's pretty unreliable. Our heat capacity has how many sig figs? 2. So I'm going to round this to 1,400 joules of energy were picked up by that. Or 14 kilojoules. What is 14 divided by 4.184? Like 3? 14 divided by 4.184. So 3.3 kilocalories, which is the same as 3.3 dietary calories. We put the same amount of vibrational energy into that as equivalent to eating 3 calories worth of food. Which is not much, is it? No, you can't even like do a push-up with 3 calories of food. All right. The next example is the exact opposite. We have this piece of aluminum, and we're going to put some water in it, and we're going to warm up the water with the aluminum. Which is kind of a weird idea. I need water. All right, so I have some water. Has the temperature of the aluminum settled down yet? 54.6? All right, what's the temperature of the blue, which is the water? 21.6? All right, so we're going to write those down. The initial temperature of the water is 21.6. This is not in your notebooks, people at home, or here in class. This is just on the board. The temperature of the aluminum we're looking at is 54.5. We already did the mass of the aluminum. This 500 grams. I need to know the mass of the water. But the only way to know that is to pour the water in there. Let's see, that is... Oops, wait. So that is 17 grams of water, and those temperatures are changing on our scale there. For you people on this side of the room who can't see, the temperatures are, one's going down and the other's going up, right? The water is the blue one. Is it increasing? The aluminum is the red one. Is it decreasing? At the surface, where they're interacting... Oh, good, Kristen. You and I are going to do something. Okay, do like this with your hand. Yeah, like that. Okay. If we actually got too close... No, we're going to smack each other's hands. Not like hard. Don't hurt me. Okay? Like, just do this. Stay, all right. As they come close together, they start hitting, and eventually that energy is transferred. Wait. You can hear the actual hand. There we go. Now, eventually they become the same temperature. Stay with me here. Stay with me. They become the same temperature, and they're vibrating at the same speed, and the temperatures are the same. If they're not the same, would they be synced up? And then they would hit, and they would start to push each other around until they got synced up. Right now, you can go sit down, yeah. Right now, at the surface, the hot ones are smacking the cold ones, and the cold ones are going, oh, quit it, until they come to the same speed. Are they getting closer together? Have they just about stopped changing? Peeking. So we currently have 52 and 50 as the two. What's odd is the cold one, the water, now looks like it's hotter than the one that was hotter, right? And that is a little weird. The temperature probes are off. They weren't exactly perfect to start off with. This one currently says 52, and this one says, what? 49? Oh, man. 49. So I'm going to pause for a second while from this side of the room over that way, you guys are in charge of figuring out what aluminum just did. From here over, you're in charge of figuring out what the water just did. Spoiler alert, this answer and that answer should be almost equal. They won't be equal because we're losing some to the air, but almost equal. All right, let's hear what the people have to say. Let's call on Yasmin. How you doing, Yasmin? You had a good day? Yeah. So Yasmin's going to give our Q for aluminum. She's doing the mass times the heat capacity times the delta T, which is negative. The delta T is negative because it's getting colder. It's losing energy, so we should have a negative value in there. It's losing energy, so we're expecting a negative Q. What did you get? .5? All right. And over here to my favorite Mina in the whole class. She's got 17 times 4 times 30. This is going to be positive because the water was gaining the energy. Its temperature was increasing. Unlike the aluminum, which was losing it, she is typing vigorously on what could be called a calculator. She's trying not to laugh. I'm recording this, you know. 2,000, slow down. 160. I consider this to be a success. Whew. I'm happy about that. So the water is losing 2,400 joules. Subtract, idiot. The aluminum is losing 2,400 joules. The water gained 2,100. That's not equal, is it? Where's that other bit of energy going? The air. Yeah, if you put your hand above it, you can still feel that it's giving off heat. Some of it does go into the air. We would like them to be equal. I'm going to write down Q of air equals about 300 joules. That's where the missing 300 is, possibly in the air or in the styrofoam, right? It's in a styrofoam container. We use styrofoam because styrofoam's not very good at taking energy in because it's filled with gaps of air. It's actually like fluffy air. It's air inside little chemicals. Almost done. We got a couple terms here. We have enthalpy. Was there actually a reaction that just took place? There was no reaction, was there? But I want you to imagine a world in which someone has a cup of gasoline and they have a bucket of gasoline. All right? Which of these things is going to give off more energy? The cup or the bucket? The bucket's going to give off way more energy, right? So let's just pretend that this gives off 20 joules and this gives off 200 joules because it's 10 times more gasoline. So this is 1 cup and this is 10 cups. It's a lot bigger. But look at that ratio. 20 over 1 is the same as 200 over 10, isn't it? The ratio of energy to quantity is the same. That's what enthalpy is. And this is missing from your notes. Got to add a per mole here. Per mole. These reactions are per mole. It releases 395 joules for every mole that reacts. It takes in 198 kilojoules for every mole. Or to put it in a perspective that some people understand a little bit better, you have an ice cube and your buddy has 10 ice cubes. Which one takes more energy to melt? 1 or 10 ice cubes? 10 ice cubes. But the ratio of energy is the same. The ratio of energy per cube is the same. And that's what enthalpy is. It's the ratio of energy per mole. Enthalpy, represented by the delta H, is the ratio of energy per mole. Calorimeters are ways of measuring energy. It's the easiest, like calorie is energy, meter means measure, so it's energy measurer. We will make a calorimeter for our lab next class. We'll use a styrofoam cup, water, and a thermometer. Right? It's pretty easy. And then we're going to take a super hot piece of metal and put it in the water. The water gets hotter. That means the metal got colder. And we'll be able to figure out exactly what happened energy-wise. Entropy we don't do too much about. Entropy is a measure of disorder, how organized something is. Last week, Tommy had to clean up his bedroom. He put everything back. He actually hired a professional OCD person to organize his bedroom. Even the socks are alphabetized now. Yeah, alphabetized. Everything is perfect. There is nothing out of place until Tommy arrives. So for a minute, it is perfect, and it has no entropy. It has no disorder. And then Tommy walks in the room, throws his hat in the corner, kicks his shoes off in different directions, jumps on the bed, and messes up perfection. And the disorder is growing. The entropy is growing. As we talk about disorder, we're going to primarily just compare some basic states of matter. Which do you think would be more disorganized? A solid or a gas? Gases are moving around random, aren't there? There's no organization at all. Gases have the most disorder, and we have this amazing diagram of ice, water, and vapor. Water vapor has no organization. They're not connected to each other. Solids are actually highly organized and occasionally make really beautiful things we call snowflakes in the north. Look, that looks more like a spider web. But, and the other problem with that snowflake, do you know the other problem with that snowflake I just drew? It looks like a spider web, I know. What? Yes, it's not symmetrical, but snowflakes are always multiples of 6. Always multiples of 6. There could be 6, 12, 18 points or something like that. But it's based off of the molecular geometry of the water molecule at 108, 105 degrees. So they always build together to make these perfect 6-sided, 12-sided, or 18-sided snowflakes because of the hydrogen bonding between the water molecules. This is a simple exothermic, endothermic graph. Take a look. We start here. We end there. Do we have more at the beginning or the end? At the beginning. Yep, good job. So this is an example of giving off lots of energy. Can you think of a reaction where lots of energy is given off? Explosions. Yeah. Explosions look something like this. Prepare for loud noise. Okay? Just prepare for loud noise. Tick, 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 BAM! And then all of the energy is given off, and the resulting ashes have like no energy, do they? They've lost all their potential energy. This is really a potential energy axis here. On the other side, this is an example of kind of what you guys do with food all the time. Your body breaks apart the food, reorganizes it, and turns it into things that have more energy to be used later. And the products have a little bit more energy that you can break apart later as they organize them. Things that are exo or endothermic, a lot of times people have struggled with some of them, like burning sugar is definitely exothermic. You're burning something, you're breaking it apart, releasing that hidden energy inside. Candles, definitely exothermic, lots of fires. Making an ice cube. Making an ice cube is an exothermic process. You have water, you take energy out, and then it becomes a solid, an ice cube, right? You have to take energy out. Whereas melting an ice cube is endothermic, you're putting energy into it. All right, that's it for today. Let me pass out